Hello, I am JD and you're listening to The Ongoing. In this episode, we are talking about Auguste Kekulé and his work to understand the structure of benzene, one of the most puzzling molecules of his time. The molecular structure of benzene puzzled me when I first encountered it. However, I accepted the structure as it was presented. But the puzzle stayed quietly in the background. Why this molecule and not another was structured the way it was? To understand how that question was finally answered, we have to go back. In the mid 1800s, chemists were trying to understand how molecules fit together to make molecules. They couldn't see molecules directly, so they inferred structure from how substances behaved. Auguste Kekulé was a German chemist working on this problem. He believed that chemical structure, the hidden architecture of atoms, was the key to understanding why substances behaved the way they did. He had already helped establish the idea that carbon atoms could link together into chains and branches. That insight explained an enormous range of organic compounds. But one well-known substance proved especially difficult to explain: benzene. Its formula was simple: C6H6. 6 carbon atoms and 6 hydrogen atoms. Yet no matter how chemists arranged those atoms on paper, the models failed. And while benzene wasn't the only compound that caused trouble, it was the clearest case where existing ideas about molecular structure simply did not work. Chemists at that time understood that atoms could be connected by single, double, or triple bonds. And those bonds mattered. They influenced how easily a molecule would react. Most organic molecules with multiple bonds react readily. They break apart, rearrange, and combine at specific positions. Chains and branches usually have clear weak points, places where reactions happen faster or more often. Benzene didn't behave that way. Its reactions were slow. And more importantly, they were symmetrical. No matter where chemists tried to react with it, benzene responded the same way. There were no preferred positions, no obvious point of attack. That was the puzzle of benzene. If benzene were a chain or a branch structure, some parts of the molecule should have been more reactive than others. Every experiment pointed to the same conclusion. Benzene was unusually stable, balanced in a way the familiar models could not explain. Kekulé drew structure after structure, trying to force benzene into known patterns. None of them worked. He once wrote that benzene resisted every effort to be understood. Years of diagrams and calculations had left him no closer to a satisfying answer. And still he couldn't let it go. One evening, after hours spent at his desk, he settled into an armchair near the fireplace. Notes and sketches were scattered across the floor. He closed his eyes just for a moment, and there, in that half-waking state, between sleep and awareness, he saw something unexpected. He imagined atoms, small glowing spheres, dancing in front of him. They formed chains that twisted and curled, folding back on themselves like ribbons. And then, in his mind's eye, he saw a snake seizing its own tail. A circle, a closed loop. When he woke, Kekulé wondered whether he had only imagined it. Some trick of a tired mind. But the more he thought about it, the more the idea made sense. Benzene wasn't a linear or a branch structure. It was a ring. This was a radical proposition. The notion that 6 carbon atoms could join in a closed loop, linked by alternating single and double bonds, was almost unthinkable. Kekulé didn't accept the idea because of the dream alone. He tested it against everything he already knew. The ring structure explained benzene's symmetry. It explained why all positions behaved the same way. And it explained why the molecule was unusually stable. When he published his model, many of his colleagues were skeptical. They called it a speculation, a dream, not a demonstration. But over time, the evidence began to accumulate. Experiments confirmed that benzene symmetry and stability matched exactly what a ring structure would predict. Chemistry has refined this picture since Kekulé's time, but his insight laid the foundation. Some scientists later wondered whether Kekulé was simply lucky to see that image. But most agree it wasn't chance alone. He had studied benzene so intensely and for so many years that even when he rested, his mind kept turning the problem over. In a way, the dream was just the moment when all that thinking finally connected. He could have ignored it. He could have decided that dreams have no place in science. But he didn't. He paid attention. He considered whether this strange picture might be what he had been missing. That part stays with me. Kekule's work shows that persistence matters. Coming back to a question again and again, even when it refuses to resolve. And it also shows that sometimes, when you have done the work, the mind keeps searching on its own. You may not always find the answer by force, but if you stay close to the question, keep turning it over, an idea might eventually show itself, quietly and unexpectedly, in a form you didn't plan for. And when that happens, it's worth pausing long enough to see if it might be the connection you were waiting for. Thanks for listening. I am JD and this is The Ongoing.